Thank you very much, Taras. And if I might reiterate Stephen's welcome to everybody, and particularly our younger colleagues. You are the most welcome of anybody here. Thank you very much. Okay. Well, I'm going to talk about this fundamental construction in our subject, the Davis-Januszkiewicz construction, which is the way that we understand toric varieties and all that's come from that from a topological point of view. And but the polyhedral products, the moment-angle complex is running in parallel. And so there are many things that are visible to us from the polyhedral products approach, which were troubling because we could not see those in the Davis-Januszkiewicz approach. So it turned out that we can reconfigure the way the Davis-Januszkiewicz construction works, and then those properties, so those constructions which were visible to us from the point of view of moment-angle complexes and polyhedral products, to be exact, became visible in the Davis-Januszkiewicz construction as well. Okay, so let me begin at the beginning. The references for this introductory part of the talk are the famous paper of Davis and Januszkiewicz and the excellent book of Victor and Taras. And also, for the polyhedral products, there is a survey article on polyhedral products that those of you that are not so familiar with the subject might wish to consult as well. Okay, well, here's how the subject begins. The subject begins because the circle acts on the complex numbers. Here are the complex numbers. The circle acts by rotation, and the quotient under the circle action is this object here. It is a combinatorial object. See, it has a face here. So this is the whole story right there. Circle actions convert into combinatorics, right? That's it. Pretty much the end of the story. And of course, this extends, right? And so this extends to, in an obvious way, to Cn goes down to Rn plus. And by Rn plus, I mean the positive octant. So if this was C2, it would go down to this. These are faces. And this is what we call the standard action. The standard action, and that is the content of the subject, or the beginning of the subject, and everything follows from this. So if I might just turn off the lights here. I'm going to get it. By the way, this brace is a stage prop. There's nothing actually wrong with me, but it's an application of moment-angle complexes. So you might want to check it out. Okay. Now, here's a definition, sort of. It's a definition of a toric manifold, right? And these are the ingredients of the definition. It's a manifold, an even-dimensional manifold, and it has an action of the n torus. So the n torus is acting on this 2n dimensional manifold, and the manifold has to be covered by local charts Cn, this Cn. So covered by local charts Cn, And the quotient by the torus action has to have the structure of a simple polytope. So in other words, on each patch, we get one of these gadgets, right? And when I take the whole projection by the torus action, all those combinatorial pieces over there, they have to fit together to give me a simple polytope. For example, see, look, here are three pieces. 1Rn plus, sort of, 1Rn plus, 1Rn plus. And that gives me this simplex, which is a polytope, right? So you cover the manifold with charts. You cover the manifolds with charts. Each chart projects to one of these, and those pieces have to fit together to give a polytope. And the final, oh, Taras, I'm sorry. And the final thing is well, each copy of Cn must project to the Rn plus neighborhood of a vertex of the polytope. And as Martin said this morning, simple means that at each vertex exactly n facets meet. Okay, so from the topological point of view, how do we make one of these things? Well, the ingredients are a simple polytope. We start with a simple polytope, and there it has m facets. M is always the number of facets, and n is the dimension of the polytope. So the fact that M is simple, and Martin pointed out this as well, means that every face can be uniquely given by an intersection of facets which contain that face. So that's the first ingredient, is this simple polytope. Now we need another ingredient. Those of you who are toric geometers, you know that the combinatorics of a fan does not determine the toric variety. You need to worry about the angles of the cones, right? You need to worry about the lattice. And so that's not enough information to make a toric gadget. So in addition, we require something called a characteristic function, which is a map from the set of m facets to the n lattice, and we think of it as a matrix from Zm to Zn, an m by m matrix. And we require this function, this matrix, to have a regularity condition. And the regularity condition, so here's our matrix. Let me just show you the shape of our matrix here. So the additional piece of information is we need this characteristic map, and it's an n by m matrix. So each column here corresponds to the value on a facet. So there are m columns here, right? And each column corresponds to the value of the characteristic function on the facet that's labeled by that number. Now, the regularity condition, in this case, it translates. The regularity condition means that if I have the n by n minors, which correspond to an n-fold intersection at a vertex, so that gives me an n by n submatrix, the determinant of that matrix has to be plus or minus 1. And that translates into, if f is given by this intersection of facets, then the vectors corresponding, given by the function lambda, they must span an n-dimensional submodule of the n lattice, which is a direct sum end. Okay. So now we started with a simple polytope, m facets of dimension n, and we've associated to it a function of this sort. And so now we have a fan. In essence, we have a fan, but as topologists, we don't know that. We don't know what a fan is, right? So, now we have a fan. Would anybody like to ask me a question about that? Oh, it's off that I want. Sorry about that. Problem distinguishing parity. Okay, what do we do then? Well, a function lambda, by considering Rn as the Lie algebra of the n torus, the map lambda associates to a codimension L face a certain subgroup of the n torus. So specifically, I have a face Fij, and there is the vector corresponding to the face. And this formula, the details don't matter, but this formula translates that face into this rank L subgroup of the n torus. So a face of codimension L is translated by lambda into a subtorus of rank L by this, just in an obvious way. Okay, so now I have my polytope, I have my characteristic map, and I have the way in which the characteristic map associates to each face of any codimension a subgroup of the torus. They are the three things that I have so far. And now I'm going to work with those things. And so I'm going to work with those things, those three things, and I'm going to make my toric manifold, right? Okay. So I start with the Cartesian product of the n torus with the polytope. Well, things are looking good, pretty good, because n plus n is 2n, so I've got the correct dimension, right? I'm okay so far, right? And now I'm going to define an equivalence relation on this, which I think I called in this notes tilde lambda. The equivalence relation depends on this lambda. Okay, so what do I do? Well, it's very helpful to think of Tn times Pn as a trivial bundle, right? So here is my polytope, Pn, and associated to each point, I have an n torus, right? So I'm going to think of it like this, n tori. These vertical lines represent n tori. So this is the product of a polytope with n tori. And so the equivalence relation that I'm going to describe, it consists of collapsing these tori, these red tori, to smaller tori, according to a certain recipe. I'll come back to that picture. So the first thing is, we're going to define an equivalence relation by, so an element G in the torus and a point P in the polytope is going to be equivalent under the lambda equivalence with another point in another element of the torus and another point in the polytope. And they're going to be equivalent if and only if you're talking about the same point, right? You've got to be talking about the same point. So this equivalence relation, it's going to act vertical-wise. It's going to act fiber-wise, right? There's no mixing around of the fibers in the equivalence relation. So that's the first thing. And another thing is, for most of this product here, most of this total space, for most of this total space, nothing happens. The equivalence relation mostly does nothing, right? It mostly does nothing. So whatever you end up with is going to look roughly like, a polytope crossed with a torus, right? And nothing's going to happen, except in a limited number of cases. And so here, what does it say? Well, it's going to be fiber-wise identification, and then it's going to collapse circles above each face of any dimension. It's going to collapse circles which belong to the torus subgroup which has been specified by lambda for that face, right? For that face. Okay, so lambda is going to tell me which of these, remember, each of these lines represents an n-torus. Well, let's take a more concrete example than that, right? And I'll try to illustrate better. Here's an example. Let's do an example. So the example is, we're going to take the 2 simplex as our 2-dimensional polytope, and we're going to take our matrix lambda as 1, 0, 0, 1, 1, 1. Now notice here, n is the dimension of the polytope, n is 2, and the 2 simplex has 3 faces, so m is 3. So we are going to get a 2 by 3 matrix. So this lambda tells me that the first face, okay, so let's just draw that. I'm going to draw the same picture here. So here, in this picture, these lines, so this is P2, sorry, I beg your pardon. P2 is the 2 simplex. And these lines, n is 2, so these lines are all 2 tori. And the equivalence relation says the 2 tori are left alone except the ones that are above facets. Here's a facet. This vertex is a facet. This vertex is a facet. This vertex is a facet. This is a face. This is a facet. This is a facet. And this is a facet. Now, there's a 2 torus above this vertex. There's a 2 torus above that vertex. There's a 2 torus above that vertex. These two facets intersect here. So this codimension 2 face is given by intersecting this facet with that one. And this facet, let's say that's the one that specifies the torus 1, 0, and this one 0, 1. So this says this is the first coordinate circle in T2, This is the second coordinate circle in T2. And the lambda relation then says that at this point, I have to pinch out the two coordinate circles of the two torus as groups. Well, if you take the two torus and you pinch out the two torus, you ain't got nothing left, right? So miraculously, so now we've started to identify. Okay, so it's important that I know that the experts here are looking at the clock and wishing that it was going a lot faster than it is for me at the minute. I know that, but I need to be very clear about what this equivalence relation does before I can say what I want to say. And that's why I have to take time to do it. I know that there are people, most of the audience knows more about this than I do, but I'm going to try to live with it. So what happens here? Well, we have a point. The fiber that was a two torus is now a point. Down here, the same thing happens, but instead of taking the two coordinate circles, here the lambda says that I take this coordinate circle and I pinch out the diagonal circle. Well, as groups. So if you pinch out the first coordinate circle in a two torus, and then you pinch out by the diagonal circle as a group, you've got nothing left. And so that means that these fibers have turned into points. Now remember, nothing happens on the inside. Nothing happens on the inside. So above every point, we have a two torus. Now, we come to an edge, a facet. So the facet is determined by itself. And so instead of pinching out two circles, I'm only pinching out one circle, right? So above this facet, lambda on this facet is 1, 0. So I'm pinching out the first coordinate circle. Okay, well, if I'm pinching out the first coordinate circle, that leaves me with just a circle. So the fiber along here is a circle. Similarly, the fiber along here is a circle. And similarly, the fiber along here is a circle. So, true to my word, there was no pinching. All of these red lines stayed intact. This one got squashed to a point, this one did, and this one was reduced from a two torus to a one torus. Okie dokie, so let's see what we have left here. Well, let's look along a horizontal line for the moment. And I'm going to, maybe I'll use my slide. It's a better drawer than I am, if I may. Let's just look at my slide here. Okay, you can see the top point, the bottom point, you can see circles along the edges, and on the inside you can see two tori, right? Is that exactly what I said? But now I want you to look. Let's just look horizontally along here. Now this object, it has a circle at this end, it has a circle at that end, and it has two tori everywhere between. Now this is not the construction which Martin told you about the join, but it's an equivalent construction. In fact, I think this is the original construction of the join. And the original construction of the join says, if I want to take the join of two circles, I take the product of the two circles crossed with the interval, and then at one end I pinch out one of the circles, and at the other end I pinch out the other circle. Now this is slightly misleading, because these were coordinate circles. So this circle going around that way, but this circle, strictly speaking, should be going around that way. But I'm taking poetic license. So across here, we have S1 joined with S1, and as Martin pointed out, S1 joined with S1 is S3, the three-sphere, right? So, and across every line here, I have the three-sphere. And so I have a point and three spheres all the way down, and so that is the cone on the three-sphere, right? The cone on the three-sphere. Now, what happens down here? Well, the cone on the three-sphere is joined to this object here, which is a two-sphere. It circles all the way along, and a point here and a point here. So this is the two-sphere. In fact, it is CP1 to be exact. So this is what my product has turned into. It's turned into the cone on S3, and I'm attaching the cone on S3 to the two-sphere by pinching out circles. And that is what we call the Hopf map, right? The Hopf map. So this cone on S3 is joined to CP1 by the Hopf map, and that is the definition of CP2. That's CP2, right? So we have constructed CP2 as a topological type toric manifold, right? Okay, fair enough. That's the easiest example. Okay. And that takes us a long way, by the way. Okay, so moving right along here. And now this is the construction to which Martin alluded this morning. But I just wanted to add something to what Martin said, which is not what you see on the blackboard. I just want to augment, if I may, one of Martin's comments, if I may. I know this is killing my time, but no. Okay. See, Martin constructed the polyhedral product S3. Martin constructed the polyhedral product S3. But the way Martin constructed it is that it was D2 cross S1, union over S1 cross S1, with S1 cross D2. Now, the big deal here, the big deal with polyhedral products is this is S3, but it's the boundary of D2 cross D2. S3 is the boundary of D2 cross D2. Now, we all know D3 is the boundary of we know that S3 is the boundary of D4, right? S3 is the boundary of D4. But if you say S3 is the boundary of D4, instead of saying S3 is the boundary of D2 cross D2, you lose all the information in polyhedral products. This is the extra information. That's pretty shocking, right? Why should it make a big difference whether you got D4 or D2 cross D2? Why should that make a big difference? Well, you know, I mean, the Hopf map depends on S3 being this, for example, but I want to go into that. But that's a key point that's going to come up in what I'm talking about as well. Okay, now I want to go back to the Davis-Januszkiewicz, second Davis-Januszkiewicz construction, if I may. What did I do wrong? Oh, no. Oh, thanks, Taurus. Okay, so they make another construction which looks very like the first one. The difference is, instead of taking Tn cross Pn, I'm taking Tm cross Pn, and I'm going to mod out by another equivalence relation which does not have lambda. It has theta. It has theta, right? And what is... Okay, what is theta? Well, theta is a map like lambda, and it mapped from the m facets to the m lattice. But it takes the ith facet to the ith coordinate vector in the lattice, which means it doesn't depend on any lambda. Theta is picking out of the m torus m coordinate circles, the m coordinate circles. Lambda was not doing that, right? So this information here has no lambda in it, but it has a similar sort of thing, except that the ith facet gets assigned to the ith generator, standard generator in the M lattice, right? So we do the same, essentially the same thing, but with theta playing the role of lambda. So above facets, I'm simply going to be pinching out coordinate circles, right? That's completely determined by the polytope. This facet is the first coordinate, this facet is the second coordinate, and so on. So there is no lambda here. That's the key point. And so they mod out by this equivalence relation that's purely combinatoric in nature. There is no lambda present. Okay, I just want to draw you a picture of that, if I may. So here we go. This time it's PM times TM. Sorry, Taras, I really apologize. Okay, so I'm going to do a simple example. Let us take M is 3 and P equals 2. Here we go. Here's our polytope, my favorite. P2 is the 2 simplex. Now, again, we're going to consider the product T3 cross P2 modulo tilde lambda. Well, it looks like we're heading for 3 plus 2, a 5-dimensional manifold this time. Oh, sorry, I beg your pardon, that's the whole point, theta. Okay, so we start with every line here now represents a 3 torus. These are now T3. Once again, just like the lambda case, the equivalence relation is not going to touch anything in the polytope. Thanks, Taras. Nothing in the interior of this polytope. So we come here. Let's have a look now more closely at what this equivalence relation is going to do. It's the same equivalence relation, but with a combinatorial lambda, not a other sort of lambda. Okay, so here, at this point here, this determines a coordinate circle, this determines a coordinate circle, this determines a coordinate circle. These 2 coordinate circles intersect, so 2 coordinate circles are pinched. That leaves a single circle above this point. A single circle, S1. And similarly, there's an S1 above this, there's an S1 above this, but now there are T3s everywhere. Inside, there are T3s. And then one circle is pinched out here, one circle is pinched out there. And so we have two-dimensional tori surviving along the edges. A 2-dimensional torus survives. Along here, 2-dimensional tori. And then a circle here, okay. Well, we have just seen here that circle, circle, and 2-dimensional tori here. That means we have, along this line, we have S1 join S1, so we have a 3-sphere. This is a 3-sphere. Up here we have a circle. In the middle, we have a circle crosses the 3-sphere. In the middle, we have this circle crossed with that 3-sphere. And so this turns into a 2 torus. So going across here, I have, at each level here, I have the circle crossed with S1 join S1. And now, at this end, the circle is pinched out. At that end, the S1 join S1 is pinched out. So this is the definition of S1 join S1. And so that is a picture of the 5-sphere. So the construction gives me the 5-sphere in this case. Thanks, Taurus. And there it is here. And there was no lambda to do with that, right? Okay. Now, some of this repeats what Martin explained so carefully this morning. If I have a polytope, I can associate to it a simplicial complex. And we didn't, I'm not going to give a proof of this, but if you take a look at that survey article, which I mentioned to you, that's online, it's called Polyhedral Products and Features of Their Homotopy Theory, you can see, and probably in Taurus's book too, you can see that this object, which we have just constructed with this theta, not the lambda, is homeomorphic to a co-limit, and this is the polyhedral product, or the moment angle complex, that corresponds to the simplicial complex that comes from the polytope. And here, the moment angle complex is a subspace of the M-fold product of D2. And the beauty, the miracle of a moment angle complex is Tm is acting on this product. This sits inside this product, and that subspace is invariant under the Tm action. So that's where the fact that the polyhedral product is born of Cartesian products is helping us out, right? So that's a sort of summary of the situation where we are now. Okay. Now, you can compare the two constructions. The kernel of the lambda is going from M to N is because of the regularity condition, is Tm minus N. And this is Tm acts on this space in the obvious way, and the regularity condition ensures that the kernel of lambda acts freely on that second Davis-Januszkiewicz space. And this, see, we don't really know about this bottom part here, but here's a fact. This is the construction I just gave you. It projects, if you have a lambda, it projects down to here. It projects down to the first space I mentioned, and that is the same as, first of all, taking the moment angle complex version and then modding out by the kernel. So in the Buchstabe-Panov parlance, this is what we see. This is what we have so far. The kernel of lambda is outside here. Now, we look at this. You look at this picture, and it always troubled me when I saw this Tm turning into Tn. See, Tm turns into Tn, and you think, well, if you mod out by lambda, Tm turns into Tn, right? But that doesn't work. That doesn't work, right? But I'm just saying that heuristically, you can sort of just, this Tm should have something to do with this one in a straightforward way. Okay. And so that's where we are. That's the end of the story, right? This is, I mean, if I run out of time now, at least I have shown those of you new to the subject how we construct a toric manifold from a characteristic function and what that has to do with moment angle complexes, right? Okay, so I could sort of rest on my laurels there if I run out of time. Okay, now the main reference for all that follows is a paper written by Martin, Fred, Sam, and myself which is online. It's published in this Perspectives of Lie Theory, but it is on the archive. Okay, so we're going to modify the equivalence relations. And we're going to start with a simple polytope. And we're going to, now remember we started with the M torus, but we don't care about the M torus anymore, right? Never heard of it in my life. And instead of S1 multiplied by itself M times, I'm going to take any space, decent space, any decent space, set of M spaces that I like. But I'm going to label those spaces by the facets of the polytope, just as I labeled the circles by the facets of the polytope. And again, instead of Tm cross Pn, I'm going to take the product of these spaces, and I'm going to define an equivalence relation on that product. Now, this is going to trouble some of you, so I'll give you fair warning. And here's the equivalence relation. Many of you may not have seen it before. So if you give me a point in the product and a point in the polytope, it's going to be equivalent under what I'm calling tilde 1 with another point in the product and another point in the polytope. Once again, it's going to act fiber-wise. P has to be the same as Q. And now, just as before, if the point P is in the relative interior of this face, look, there are no tori, there are no subgroups of the torus determined by lambda, there are no subgroups of the torus anywhere in my discussion, right? So if I have the face which contains the point P and Q are the same, is given by this intersection of K facets, then I need that xis has got to be the same as yis for all s which are in the complementary facets to those which intersect to give me the face P. They have to be equal. Those coordinates have to be equal. And if they are, I say that this point is equivalent to that, and I denote the equivalence classes by this. So there's definitely no lambda, and this looks completely radical and far-fetched. Okay, what next? We're going to have a reality check. Okay, if we take xi to be S1, I'm not using any actions of the circle. If I take xi to be S1, then I do this equivalence relation, I get Tm cross Pn tilde 1, and that turns out to be exactly the same effect as modding out by tilde theta, the one that identified the coordinate circles with the facets. And that is the Davis-Januszkiewicz space. So, yes, we're in business. And not only that, but if you do this construction, what you get is the polyhedral product where this is the first space is the cone on xi and the second space is xi, right? A miracle, right? A miracle right there. There's no lambda. We are just doing the equivalence relation where in the complementary facets, coordinates have to agree. And we get this, right? So right here, there's something going on. This connects the Davis-Januszkiewicz type construction to this very special polyhedral product. Okay, so something has to be going on. Oh, I just remembered I have an hour and a half. Oh, God. Didn't have to be killing myself. Okay. Would anybody like to ask me a question? There is no characteristic map here. There's no nothing, right? We just do, I want to go back and emphasize that there's no nothing. You see here, this tilde that, if and only if the coordinates in the complementary faces agree. That's the only condition, right? Doesn't look right, does it? And there's more that you're going to worry about ahead, right? Okay, so what? Okay, now, at this point, now that I've obtained the polyhedral product of cone on x comma x, I now come along and say, what if I have a circle which acts freely on each of those spaces, x1 up to xm? What happens, right? So they come equipped now with free actions. These have to be free actions of the circle. Now, so it says, once I have that, then there is a natural free action, a free action of the M torus on that product, a free action. Okay, that's just trivial from just taking the product action. And it says, recall that the function theta indexes coordinate circles in Tm by the facets of Pn. And so this associates each space xi to a facet. It associates each space xi to a facet. Now, so an intersection of k facets, it determines because here are coordinate circles, we're talking about coordinate circles, right? So an intersection of k facets determines a projection from the M torus to the M minus k torus, right? So you give me an intersection of k facets, you've got such a projection. And so by this projection, because everything is the diagonal action, the M torus acts freely on the product of the x's that correspond to those facets. The M torus is acting freely on those on that product. So I'm going to be using this projection that corresponds to an intersection of k facets, and this works because each facet is represented by a coordinate circle. There's no lambda. Okay. So now someone comes along and gives me a lambda, same as before, with a regularity condition. The kernel of lambda is an M minus n torus. And so I get that now the kernel of lambda is a subtorus of the M torus. The M torus is acting freely. And so that gives me an induced action by going through the M torus on, we already saw that the M torus has to act on this. So that says the kernel of lambda has to act on that. Okay. So now I have these x's, I have a free action of Tm, I have an action of the kernel of lambda, and now I have a well-defined projection. Now, a well-defined projection, if you give me a face that determines this part of the product, associated to this product, there is a projection. And that projection does the following for me. So here is a quotient. This is the quotient of the whole thing by the kernel of lambda, which is acting as a subtorus of the M torus. And these are the equivalence classes. And the projection is going to take me from this quotient to this quotient. Right? This doesn't have all of the x's, that just has the x's determined by a face. And so this projection takes this equivalence class and this quotient to this equivalence class under the same action. And that corresponds to an intersection of k facets. Okay. Where do we stand now? Okay. So now it makes sense to talk about x1 up to xm modulo the kernel of lambda. That's a space, and I'm going to cross it with the a polytope of dimension n, which supports the lambda. And so I'm going to define an equivalence relation on this space, right? Now the big difference here, the big deal is I'm now defining an equivalence relation, delta 2, but the equivalence relation is on the quotient, is on this quotient, right? It's on the quotient. And the equivalence relation is going to be, these are equivalent if P is the same as Q. And if P is in the relative interior of this face called F of P, and F of P is this unique intersection of facets, right, which are complementary to, these facets are complementary to these ones. Then the two classes are going to be, then they're going to be, I beg your pardon. Then two classes are going to be equivalent if the projection onto the complementary facets of these equivalence classes are the same. So we're going back, I know I've confused you. Lambda, the equivalence class lambda, are equivalence classes in here, in this quotient. So this class here is in this quotient. And now I project out, and I project out the same projection on the other side. And if those two projections onto the complementary facets are the same, then they're equivalent. And so I have defined an equivalence relation on this, and I'm going to call it tilde 2. Now, tilde 2 does not involve lambda. Tilde 2 does not involve lambda. It is projection onto coordinate objects, right? Tilde 2 does not involve lambda, right? I can't stress that enough, because all of the projections are dependent on the labeling of the facets in a natural way. Lambda is playing no role in this equivalence relation. The classes have to agree after I do a projection. Okay, moving right along. So now I have this complicated equivalence relation. Now look, think about what this is. If this is S1 up to Sm, if this is Tm, and this is the kernel of lambda, then this looks like Tn, right? Looks like Tn. We have moved lambda into the Tn, right? That was the sort of goal, right? Okay. So the kernel of lambda acts on this space. Remember, tilde 1 is an equivalence relation that only involves theta, no lambda here. And this is the action of the torus. And you can check that this is well defined. Everything in sight has to be well defined, right? So kernel of lambda acts on this. So since kernel of lambda acts on this, I can take the quotient by the kernel of lambda, see? This mod the kernel of lambda. It turns out that that's exactly the same as first modding out by the kernel of lambda to get Tn, if you like, cross Pn, and then using the coordinate equivalence relation, not involving lambda, and these two things are homeomorphic by this homeomorphism, right? So this is under the action, the quotient action of the kernel of lambda, and this is the complicated one in terms of projections. And it's the fact that this is true, right? This essentially is the moment angle complex, and you're modding out by the kernel of lambda. But this one here, the equivalence relation does not involve the kernel of lambda. And in fact, we do not need polyhedral products to construct these homeomorphisms. They're constructed directly. Okay, so what? Okay. And so the regularity condition tells me that the kernel of lambda acts freely on this gadget. That's what tilde 1 gives me. And so we have a commutative diagram where this tilde 1 did not involve lambda, but there's a map from here to here, which I just discussed. This is the same. I pointed out to you when we defined tilde 1 that this gadget's exactly this polyhedral product, and this map across here is the quotient of the polyhedral product by the kernel of lambda. Okay, well, that's for any space X. Now, can we think of a space X? Yes, we can think of a space X. Here's a space X. Xi is the moment angle complex on some polytope Pi. Now, if you have a moment angle complex, the M torus acts on that moment angle complex, but the diagonal circle in that Tm, it acts freely on the moment angle complex. Every moment angle complex has a free action of the circle, every moment angle complex. And so, coming from a polytope, I should say. No, actually, I think it's always true. So what we're going to do is we're going to take these we're not going to do it, I'm just going to say something. If I take Xi to be this space here, the circle acts by the free diagonal action. And so if I want it to be perverse, I could plug moment angle complexes into here. I don't want to be perverse, but I could if I wanted to be. I could plug moment angle complexes into here. So you'd have ZKP of the cone on a moment angle complex, and we have written a paper about that. And very quickly, you end up in Eisenberg land with iterated polyhedral products on iterated complexes. And a lot of nice theorems are true, by the way. A lot of nice theorems are true, but as I say there, that's for another course, right? Okay, so let's recall the way we constructed CP2. We went through it in gruesome detail over here. We started with the polytope, the simplex, that's sort of bluish, and then we did the tilde lambda. This should be, I beg your pardon, this should be a tilde lambda. And so we pinched out two circles here. We did this. If I go across here, that's S3, S3. So that's the cone on S3, and the cone on S3 is glued to CP1, S2, by the circle action, collapsing by the circle action. So that's how we constructed P2. Now in algebraic geometry, in toric geometry, this corresponds to constructing CP2 with a two-dimensional fan, right? It's the standard procedure. CPN is constructed from the fan corresponding to the n simplex. Okay, so that's what we did. So now I want to do something different, right? That's CP2 that we know and love from any point of view that you like. Okay, now I want to look at CP2 from this new point of view. And the ingredients are going to be, that's supposed to be red. I changed it, but Pn is going to be a one simplex, right? A one simplex, that should say a one simplex. Now already something's going on because, already something's going on because this is a two simplex, right? That's a two simplex. Now I'm talking about a one simplex. And now I'm going to take x1. So M is 2 here, right? M is 2. A 1 simplex looks like this. Here's what a 1 simplex looks like. It's got 2 facets, and its dimension is 1. So here in this case, M is 2. N is 1. Now, I'm going to show you another picture soon. Oh, God, what am I talking? I went to the wrong page. Yeah, okay, look. Okay, P is a 1 simplex, but in the picture we're going to go to, instead of drawing the 1 simplex like this, I'm going to be drawing it like that. But there's no big deal, right? It's more convenient for me to draw it like this than it is to draw it like that. So my new ingredients are going to be a 1 simplex, and X, so M is 2, so I need an X1 and an X2. X1 is going to be S1, and X2 is going to be S3. So the circle acts freely on both of those spaces, right? The circle, remember, has got to act freely on X1 up to Xm, and it's acting freely in the standard way on S1 and S3. And now I'm going to take a characteristic function, but this characteristic function is for the 1 simplex, which has 2 faces, right? So this characteristic function is going to be a 1 times 2 matrix. Last time it was a 2 by 3 matrix, right? But now it's a 1 by 2 matrix, and the kernel of this map is a 1 torus, and it sits inside the 2 torus like this. That's how the kernel of lambda sits inside T2, as this sort of diagonal torus. So now I'm hoping to make CP2 with less combinatorial information. In other words, for those of you toric geometers, I'm going to make CP2 with a 1-dimensional fan. In fact, I can make CPN with a 1-dimensional fan. I'm going to make CP2 with a 1-dimensional fan. And here's what I'm going to do. These are my ingredients. And I'm going to draw P1 this way. Now, we have to go back a bit. Oh, no. We have to go back a bit. So look, to do this construction, I have to be holding in my hand, Tm modulo the kernel of lambda cross Pn. And then I'm going to do a projecting equivalence relation that's got nothing to do with lambda. So when I say I've got a Cartesian product that I'm going to consider as a trivial bundle, well, the red lines are not going to be n tori. Remember, I've been drawing this picture. So if I take the trivial fibration, I'm going to have above each point, I'm going to have a red line. But these red lines are not n tori. These red lines are these gadgets. See? Oh, sorry, I beg your pardon. I didn't go back far enough. I meant these gadgets. See? Normally, this would be Tn cross Pn modulo the equivalence relation given by lambda. But I am not doing that. So this is my trivial bundle, and the red lines correspond to the product of the x's modulo the kernel of lambda, right? That's what the red lines are. They're no longer Tn. Are you all with me? Well, remember what x1 is. Thanks, Tara. x1 is a circle, and x2 is the three-sphere. And the circle and T2 is acting. So the red lines are going to be x1 cross x2, x1 cross x2, modulo the kernel of lambda, crossed with P1. That's what the red lines represent. And so that is S1 cross S3 modulo the kernel of lambda crossed with P1. I haven't done the equivalence relation, but that's what it is. So each red line is one of these gadgets. So it's S1 cross S3 modulo the kernel of lambda. Now,
the second factor is S3.
Oh, sorry, I beg your pardon. Thank you, Taras. S3. S3, I beg your pardon, that's a typo. Now, nothing is going to happen in the interior of the polytope, so these are going to stay as they are. These things are going to be left alone by the equivalence relation. But these two are not, right? So each one of these, now what is this? The kernel of lambda, in our case, it's okay, Tara. The kernel of lambda is a circle, and the circle is acting diagonally on this. And as Martin mentioned earlier today, the circle acting on this is homotopy equivalent to, actually more than a homotopy equivalent, let's just go, is homeomorphic to, sorry. It's homeomorphic to S1, S3. So each one of these red lines is going to be, nothing's going to happen to it. So it's all S3s. Okay. So here is the first facet. So we have to project from this to S1 modulo the kernel of lambda. That's what the projection does. We're going to project according to the first facet, and then we're going to project according to the second facet. So the map sends, the projection sends, goes from here to S1 modulo the kernel of lambda. So this is going to be S1 modulo the kernel of lambda. And of course, that is a point. So the red, I should keep everything red. The projection gives me nothing. Now, at the other end, nothing happens. These are all S3s. At the other facet, we are going to project onto the second factor. So we're going to project S1 cross S3 modulo the kernel of lambda. Now, this doesn't happen for all group actions. You can't take any old group action and do what I'm doing. It wouldn't be well defined, right? But it's because everything is coordinate-wise, right? And I have the diagonal action. That's what's making it work, right? Okay, so down here, I have to project onto S3 modulo the kernel of lambda. Remember, it's acting with degree 1 because it was acting diagonally, and this is CP1. Or if you like, we won't see it as this necessarily, we'll see it as S2. Okay, so down here is going to be an S2, right? Because I'm projecting, this gadget's untouched. Up here I project onto the first X, down here I project onto the second X. This gives me S2, right? I project onto the second X. Okay, let's look at the picture now. Okay, Terrace, thank you. Here we go. Where am I? Oh, what did I do wrong? Oh, here we are. Okay, here is the simple polytope. At the top, I've projected onto the first factor a point. Here, I've projected onto the second factor. And what do I have? In the middle, I have S3, right? Because the circle is acting diagonally, and it's easy to produce a homeomorphism from this to S3. So this is the cone on S3, and it's attached to CP1. But here's an interesting thing. Here's how is it attached? No need to turn off light. How is it attached? It's attached by this projection. And that projection is exactly the Hopf map. That projection is the Hopf map. So this, a cone on S3 is attached to this by that projection, and so this must be CP2. So we constructed CP2 via a modified Davis-Januszkiewicz construction. This is the tip of the iceberg, by the way. But by rearranging the equivalence relation to avoid lambda. Now, what is going on here is a good question. What is going on here? Well, here is what is going on here. And if I start treading on anybody's talk, please stop me. Please stop me, and I don't want to tread on anyone's talk. Even, could we have it back on? This is the last time, Terrace. Okay, what is going on here? Well, what is going on, I sort of hinted at it, is if I take Z of corresponding to the interval, say, and if I take Z of P1, KP1. Now, I want to put here, now remember, this has got two facets, M is 2, so I have to give you two pairs. And the two pairs I'm going to give you are D4 S3, comma, D2 S1. I'm taking this space and I'm modding out by the kernel of lambda. In a way, let's put this in inverted commas. Not as easy, I have to write down what the matrix comes from lambda, but let's put kernel of lambda in inverted commas. It's not strictly speaking true. But this space here exhibits a very important property of polyhedral products, which is called the exponential property of polyhedral products. And so this turns out to be the same as Z K of P2. K of P2, so this time I've got three facets. Right, and this is what we were observing, and that's the explanation from the point of view of the Davis-Januszkiewicz space. Is anybody going to be talking about the exponential property? Well, I'm going to tell you, I know I'm not supposed to be talking about polyhedral products, but I'm going to tell you my favorite polyhedral products theorem, which has not been recognized yet as a great theorem. So I'll tell you what that great theorem is. I'm about to say something wrong. That's the hint I'm being given, Martin. Did you do that, Martin? Here is a great result about polyhedral products, which is yet to come into its own. Well, it does this for us, and that is, if you have a pair XA, two pairs XA and YB, two pairs, you can make the Cartesian product, right? And that is X cross with Y, then X cross with A, union over A cross, X cross with, beg your pardon, X cross with B, union over A cross B with A cross Y. That's an operation on pairs, right? And so, this is the amazing thing, and if this were the problem session, I would ask the question, why? Why, right? It turns out that simplicial complexes can detect this operation. Now, how would a simplicial complex know that you've been taking Cartesian product? Well, it turns out that now, if I start with an xi ai, I can raise it to the exponent ji for any ji. Just multiply it by itself, ji. And so I can make a new set of spaces. So if you give me the xi ai's, I can make new pairs yi bi to the yi bi. I can go from this pair to this pair where yi equals yiai bi, equals xi ai raised to the exponent ji. That's an operation on pairs. Well, it turns out that if you give me a string of ji's, everything is m, length m, right, as usual. So if you give me a string of ji's, j1, j2, up to jm, and so I make these yi bi's. So here's a theorem. Given k, a simplicial complex k, and j, a string of integers, positive integers, right? We can make a new simplicial complex. We can make a new simplicial complex. We can make a new simplicial complex, and that new simplicial complex we call, it's much bigger, it's called k of j, right? K of j. And here's the theorem. Here's the theorem. The theorem is that I've got the original simplicial complex, I've got the k, I've got the j, and I've got k of j. And the theorem is that zk, try doing this in the other notation. Zk, oh, you can. YB. So the y's and the b's are the exponentiated. These are the big pairs. This is the small simplicial complex. That is equal to, not isomorphic, not homeomorphic, equals Z. Now, okay. Now I'm going to put something up, but you can challenge me on it, right? Xk of j of the yb. Now you could say, well, Tony, that doesn't make sense because this is m and there are m pairs. Sorry, xa. These are the unexponentiated. And you could say, well, that doesn't make sense, Tony, because you've got m of these, but the m for this is much bigger, so this doesn't make sense. But what I mean here is instead of x1, I would take j1 copies of x1, right? So it does make sense. So, you know, I'll just put inverted commas. And that's what's going on here, and that's what I'm trying to explain with this. We can see that if we reinterpret the Davis-Januszkiewicz construction, right, and generalize it, you can. And now, actually, there have been applications of this outside our subject. Now, it turns out that Michael Wehrmeiler has studied SUN to the wazoo, and it has things to do with this. Has things to do with SUN manifolds. It says something about SUN manifolds and SUN bundles, which unfortunately I didn't brush up on before my talk. But it has applications, the fact that certain spaces can be realized in these two different ways. You want to think of this as the big fan way, and this the small fan way, but S1 cross S3 here, D1 cross D3 here. This is just D1s and D2s and S1s, right? So, well, thank you very much for your attention.